What's up, everybody? This is section 5 of the final review. We're talking about integration. And I'll start with problem 30, which has us compute some integrals from the limit definition, right? So, in other words, using limits of Riemann sums. And I'm not going to do part A and part B because those, we've done plenty of examples like that in tutorial. So I'll just skip over those. But I do want to do part C, which is an interesting approach to finding an integral, right? So I'm integrating the function e to the x between 0 and 1. And of course, using the fundamental theorem of calculus, the answer that I should be getting is e to the x evaluated from 0 to 1, so I should be getting e minus 1, right? We'll see if this is the answer that we obtain. So I'll start with the integral 0 to 1 e to the x dx. This should be the limit of the Riemann sum, and I'll do a this time I'll do a left endpoint Riemann sum because it turns out that the math works out a little bit easier that way. So I'll start by saying this is e to the function I minus 1 over n, because the delta x is going to be 1 over n times 1 over n, right? So that's the Riemann sum that I'm looking at. And the idea now, I goes from 1 to n, is to use geometric series to get a closed form limit
as n goes to infinity. Take out the constant term that doesn't depend on I in front of the sum, times the sum I goes from 1 to n. And in order to turn this into a geometric series, I have to have a constant to a power, right? So what I'll do is I'll have e to the 1 over n to the power I minus 1. So I have the constant, which is going to be the common ratio for the geometric sum to a variable power. And I know this should be the 1 over n stays. The closed form for a geometric series is the first term, so when I equals 1, the first term in the sum is this to the power 0, so it should be just 1, minus the last term times the ratio. So the last term is e to the n minus 1 times the ratio again, so it's going to be to the n, so it's going to be e to the n over n. Or we can, let me actually write it 1 over n to the power n, like this, which is going to end up being just n to the n, n over n, divided by 1 minus the ratio, so 1 minus e to the 1 over n. So this is the closed form for this sum, using just the geometric sum. Okay, what does that equal to? Let's see. This is the limit as n goes to infinity, 1 over n. On top I have the constant 1 minus e, because this is going to be the nth root of e raised to the n power is just e, divided by 1 minus e to the 1 over n. And I'm going to rewrite that now as the limit. I can actually bring the 1 minus e in front, and I want to also flip the order of these, so I'll actually write it as e minus 1 times the limit, because that's just a constant, n goes to infinity, 1 over n divided by e to the 1 over n minus 1. And notice as n goes to infinity, the quantity 1 over n goes to 0, so this is the same as e minus 1 times the limit of, let's say, y goes to 0 of y divided by e to the y minus 1, right? So I'm thinking of this 1 over n as a variable y going to 0, and that's how I obtain this result. So now what ends up happening is simply I use the special formula that's given in the hint, that the reciprocal of this goes to 1, which means the thing itself goes to 1. So this should be just e minus 1 as the final answer for the limit.
which is exactly what we got when we computed this using the fundamental theorem. So it does work out. So that's problem 30C. Let's move on to problem 31, and I'll do part A. I'm looking at the integral from 0 to 1 of 1 over x squared plus 1. And I recognize that this is the derivative of arctangent, so using the fundamental theorem, this is arctan of x evaluated from 0 to 1. So it's arctan of 1 minus arctan of 0. Now arctan of 1 is basically going to be for what angle theta is the tangent of that theta 1, and that happens at 45 degrees, right? And that's exactly pi over 4. And arctan of 0 is just 0. So this is the answer for part A. Let's do part B. This time we have the integral from 2 to 3 of the function 5x to the 4th minus 2x all over x to the 5th minus x squared dx. And notice the bottom has derivative the numerator, so the antiderivative of this should be natural log of x to the 5th minus x squared. And of course you could do this the long way using the substitution u equals x to the 5th minus x squared. You get the same thing. And I'm evaluating this since I'm back to variable x, I don't have to change the bounds for the substitution, so I just evaluate this between 2 and 3. So the answer should be, well, when I plug in 3, I get ln of 3 to the 5th minus 3 squared divided by 2 to the 5th minus 2 squared. And the reason why it's like that is because it's ln of the top minus ln of the bottom. And of course, when I have the difference of logs, I can simply take the ratio, right? If I have ln of a minus ln of b, that's the same as ln of a divided by b. And of course, you compute this, you get some number. It's not some particularly special value, it's just this. So I'll leave it in this form. Part C, let's flip the page. So part C has us now do the integral from -1 to 2 of sine of x e to the cosine of x dx. And of course you could do the substitution, u equals cosine of x, change the bounds, do all that. But I'm not going to spend time doing that here. We've done plenty of examples in tutorial to see how the substitution technique is used. I'll simply write the antiderivative here. So this should be e to the cosine of x. When I take the derivative of this is e to the cosine times negative sine, so I have to fix that by adding a minus in front. And I'm evaluating this between -1 and 2. So this should be negative e to the cosine of 2 minus e to the cosine of -1. And because cosine is an even function, I can simply write it as cosine of 1. So this is, once I distribute the negative sign, it's e to the cosine of 1 minus e to the cosine of 2, and that's the answer for part C. Let's also do the last one. What do we have? Part D. This is the integral from 1 to 5 now of e to the 3x square root of 7 plus 3e to the 3x. And this time I'll do it the long way, just to kind of, it's not quite, there's a few constants that are happening when you take the derivative, and I don't want to mess it up. So I want to be careful, and I'll do the substitution. U equals 7 plus 3e to the 3x. I also have to change the bounds. So u of 1, the lower bound is going to become 7 plus 3e cubed
u of 5 is going to become a new upper bound of 7 plus 3e to the 15. And now I have to compute du. So du is going to be 9e to the 3x dx, and if I want to solve for dx, that means dx is going to be du divided by this, and we're ready to substitute things back in. So let's see. The bounds for the integration, the new lower bound is 7 plus 3e to the third. Upper bound is 7 plus 3e to the 15. And I'm integrating, well, I have e to the 3x here, square root of u, so I'll just write it as u to the 1/2, times the dx becomes this expression down here, so du divided by 9e to the 3x, and notice that everything that was in terms of x cancels, so I'm left with just an integral in terms of u, which I can very easily solve, right? The integral of u to the 1/2 is u to the 3/2 multiplied by 2/3. I also have a 9 in the bottom, so it's going to end up being 2 over 27, right? Because 3 times 9 is 27, and I'm evaluating this between the bounds. 7 plus 3e cubed, 15th.
And now I just plug in the bounds, right? So this should be 2 over 27 times. Okay, I have 7 plus 3e to the 15th power raised to the 3/2 minus 7 plus 3e to the third power raised to the 3/2. And this is as pretty as the answer is going to get, right? It's not going to be anything that looks nice simply because of the numbers that we have here. There are not particular special values when I plug in and get the new bounds. So that's part D, and that was problem 31. And now the last problem in this section is problem 32. And we're asked to find the antiderivatives of the following. We want to find d dx, basically, of the integral from 5 to x squared of arctangent of t. So if this is my function f of t, let's say that capital F is the antiderivative of arctangent. So this should be d dx using the fundamental theorem, we've done this in tutorial, of capital F of x squared minus capital F of 5. This is just a constant, so its derivative is 0, and I'm just left with d dx of capital F of x squared. So this is going to be 2x little f of x squared, right? The 2x comes from chain rule, so this should then become 2x. I know what little f is, that's arctangent of x squared. So that's the answer. Let's quickly do, this was part A, let's quickly do part B and see what happens. So I'm taking now the derivative with respect to x of the integral from cosine of x to minus 2 of 4 t squared plus 5 dt. So this time, this is my little f. It's going to have antiderivative capital F. So what I'm doing is I'm taking the derivative with respect to x of capital F evaluated at minus 2 minus capital F evaluated at cosine of x, the lower bound, right? This is just the fundamental theorem of calculus. Now when I take derivative here, f of minus 2 is just a constant, so that's 0. So I'm left with minus, because of the minus sign, cosine x. So this should be, the derivative of cosine is negative sine, so this should be just positive sine, because I have an extra negative here, of x times little f of cosine of x. So when I plug that in, let's see what happens. This is little f, so everywhere I see t, I replace it with cosine. This is sine of x times 4 cosine squared of x plus 5. And that is the answer. And we still have one more, that's part C. So let me move this out of the way and let's do part C. This is the last problem on the integral section. This is going to be, and let me actually use this sheet of paper here. The derivative of now the integral, and both the upper and lower bounds are variables, so I go from minus x squared to 3x to the fourth e to the t cosine t dt. So this is my f of t. Again, I apply the fundamental theorem of calculus. So d dx, the integral is going to become capital F of the top bound 3x to the fourth minus capital F of the lower bound negative x squared. And now I have to differentiate term by term because these are both functions, right? So this should be d dx capital F of 3x to the fourth minus d dx capital F of negative x squared. And when I take the derivative, this gives me 12x cubed from chain rule times little f of 3x to the fourth minus negative 2x, so becomes plus 2x little f of negative x squared. Let's plug that into the formula for little f, which is the original integrand here. So this should be 12x cubed e to the 3x to the fourth cosine of 3x to the fourth plus 2x e to the minus x squared cosine of minus x squared, and that's the formula for the derivative. And that also concludes the integral section of the review, and we only have one section left, which is applications of integral.